Okay, here is another example about discontinuity made of reactive components. So in this transmission line, we observe that there is a discontinuity in the middle of the transmission line. And here is a series capacitor. And before the series capacitor, the characteristic impedance of the transmission line is 15 ohm, and the length is equivalent to 1 millisecond of propagation delay. All right. And follow with another transmission line of characteristic impedance of 115 ohm. And now that the second transmission line is terminated with a match load of 150 ohm. This should give you a simpler analysis, which means that all the transmitted signal into the second transmission line will be absorbed by the match resistive termination. All right? And in the textbook, you can look up the entire derivation of example 6.5. However, due to the time restraint, I think I will just discuss the critical part about this example, that is the calculation of time constant. Okay? So, how to derive the time constant of this transmission line discontinuity? We know that it's a series capacitor, and we know for a capacitor the time constant is in the form of R times C. C is the capacitance of the capacitor itself. How about R? R is the resistance absorbed by the capacitor. So for this series capacitor, what is the resistance absorbed by the capacitor, the series capacitor? Well, because the capacitor is connected in series and the continuity, so it shall observe the characteristic impedance Z sub 01 in the left, as well as the characteristic impedance of Z sub 02 to the right. One to the left, one to the right, and they can be considered as a series connection because the capacitor itself is connected in series in the discontinuity. Okay, so the overall time constant can be calculated quite straightforwardly as the product of C times Z sub 01 plus Z sub 02, and C is 10 picofarad, 10 picofarad. And Z sub 01 is 50, and here is 150, so it's 200. So the time constant observed by this series capacitor is 2 nanosecond. How about for this problem? What is the time constant becomes if the capacitor becomes a shunt capacitor? Here's 50 to the left, 150 to the right. So what is the time constant value, tau, for this case? Well, C itself is still 10 picofarad. How about R? What do you think? Well, R can be regarded as a shunt connection between a 15 ohm resistor and 150 ohm resistor. What is the result? 50分之1加150分之1的导数是多少？37.5吗？好，一要假设是37.5啊。OK， 反正会比50来的小嘛，哈。So it becomes the 算这样写好了，比较保险。好， OK 啊，所以你的那个连接的方式啦，会跟那个它的那个time constant会受到连接的方式的影响啊，所以这边这个 RC 是电容所看到的 time constant。LA 呢是电感所看到的 time constant， 那一样，看你的 LA 是怎么接的，是并联的还是串联的哈，所以它看到的 R 值，即便左右两边是一样的，但是它看的有效的 R 值哈，等效电阻是不一样的 ，OK？ Alright, now let's move on to section 6.5. For the second midterm, which will take place at on November 14th. November 14th, well, 2 weeks later, we will include the scope will be from 6.1 to 6.5. All right. Okay, so 6.5 line with initial conditions, which means the transmission line is somehow charged to some degree, and we need to continue the analysis based on the so-called initial condition. Previously, the cases we have discussed so far are uncharged transmission line circuit, but this is not necessarily the case. We can continue the analysis with certain initial condition. If you have enough description about the condition on the transmission line, of course you can use all the information we have to proceed for the analysis. Okay? So in this case, we have a piece of transmission line. The characteristic impedance is 50 ohm. The length or the duration for propagation delay is 1 microsecond, which is about 200 meters. And the transmission line is open terminated at both ends. Open terminated. And the problem provides some initial condition about the total voltage on the transmission line and the total current on the transmission line. Note that, what is total voltage? The total voltage on the transmission line shall comprise two components, the forward going part and the backward going part. V plus and V minus, the two components, right? And so is for the total current. Note that on this graph, you can see that the voltage is not evenly distributed. The current is not evenly distributed as well. So what does this result suggest? This suggests that the energy, there is some energy still bouncing back and forth, going to the left, going to the right, within on this transmission line. The signal is still flowing. They are not settled. And another thing that you should be careful is about the boundary condition. For this case, the figure shows that the two ends of the transmission line are open circuit. What are the boundary conditions for open circuit termination? Well, there's a very simple rule of thumb for circuit analysis. If it's open circuit, which just suggests there is no current at that point, right? How about short circuit? The short circuit suggests the boundary condition is that there is no voltage difference at the short circuit location. So we can check up the graph to make sure that this problem is given correctly. you see that the current at the right end is 0 amp, the current at the left end is 0 amp, which complies with the condition provided by the graph. Now, they are open circuited. And because they are open circuit, the voltage on the two ends can be any arbitrary value, but for the currents, they should be 0. On the other hand, if you should terminate it at the two ends, what is the boundary condition required? And that will be the voltage, if they are short-ended, the voltage here should be 0, the voltage here should be 0 as well. So before you proceed for the problem, you should check up the boundary condition. And this problem looks fine. Alright, so we know that on this dual-end open transmission line, the voltage and currents are not evenly distributed. There are some which suggest there are something going on the transmission line. So what we would like to do is to kind of decompose the total voltage and total current composition into forward going and reverse going part. Okay, so as you can see from the problem, from the description, it provides you the circuit, it provides you the total voltage, V and I. So we like to find out the V plus components, V minus component, I plus component, I minus component, right? And we also know that V plus and I plus components are related by the ratio of characteristic impedance. So in fact, we only have two unknowns. Okay, so here we write up the relationship. The first one is total voltage relationship. V equals to V plus plus V minus. I equals to I plus plus I minus. And this equation should be satisfied any place, any location on the line, okay? So here you have a description. Here we are talking about the initial condition. So you see the time instant specified in these two equations are t equals to 0, that is the initial time. However, the position z is not specified, which means this relationship should be satisfied any place on the transmission line, okay? And because we know that for the I plus part and I minus I plus equals to V sub 0 over Z sub 0 and I minus equals to minus of V sub 0, V minus over Z sub 0. So this equation can be transformed into using description of V plus and V minus. Okay, so that's the reason why I say that you have only two unknowns, V plus and V minus for the two equations. And the total voltage then can be written in terms of the two equations as V plus equals to 1/2 of voltage plus Z sub 0 times I. And so similarly, you can express the V minus signal using this equation. So we massage a little bit about the two equations in the previous slide and end up with the description for V plus and V minus signal. All right? Why bother to find out V plus and V minus signal? Because the trick in this problem is it's asking you what the distribution of voltage and currents becomes after a certain amount of time. And we know that there are signals, some part of the signal goes to the right and some part of the signal goes to the left. And because the two ends are terminated with open circuit, so they will get reflected. So things will continuously going on within the transmission line. Right? And we would like to know after a certain amount of time what happens with the total voltage and total current on the transmission line. Okay? Alright, so here we would like to find out the spatial distribution of a V plus signal and V minus signal. Note that the problem provided in this case are made up, are shown in these figures, are shown in this graph, shown in this plot. This kind of plot has a specific name. They are so-called piecewise linear. 线性连续还是线性不连续？我忘记了，不知道怎么讲。反正它们都是直线嘛，只有在特定的位置有转折，所以这种图形叫做 piecewise linear。那好处就是说，你在算的时候，只要算这些转折点就好了，那中间就是顺着内插还是外插过去好，所以就是说，你只要解中间、左边、右边这3个点，就可以得到完整的表示。所以意思就是说，你要去解3组的2元流利方程式，在左边、在右边、在中间。你要解出在左边的 v 正 i v 负，中间的 v 正 v 负，还有右边的 v 正 v 负那解这件事情当然其实也不难嘛，2元联立而已，所以就看图把数目字带进去就好了所以这边看到的是这2个式子是在最左边的最左边的。事实上你就是把 v 正的电压是50嘛 ，z0 是50嘛。I 在这个位置是0嘛，所以套进去得到的 V 正是25，然后在这个地方的 V 负同样套进去是25，所以25加25等于50。OK， 所以这个简单的算术对各位应该不是问题嘛，所以用同样的解2元联立方程式，你可以找到中间的 V 正 V 负，还有右边端点的 V 正 V 负。那找到左中右3个位置的 V 正 V 负可以得到什么？你可以画出这2个图这2个图呢是在 t 等于0的这个时间点，在传输线上面的 V 正讯号的分布。最左边是25伏，中间是50伏，右边是0伏。OK， 对于 V 负讯号呢，它是最左边是25伏，中间是0伏，过来呢也是0伏，所以加拢无。好，然后另外你可以知道的是，我这边画的红色箭头，不知道为什么，因为 V 正讯号是由左往右跑所以我们把它标那几个转折点，标出 A、B、C， 那什么意思？随着时间的推移 ，A 会怎样？会撞到右边的 open circuit， 然后接下来过了，这整段是多长？1个 microsecond 吧，好像是吧？然后经过半个 microsecond 的话呢，你就会怎样？你就会那个 B 点就会跑到右边，那经过1个 microsecond 的话呢 ，C 点会跑到右边，那 C 点在一开始的时候呢，在这边的 C 点呢，它会往左边跑，但是它左边已经是 open circuit 了，所以这个讯号会怎样？会接到右边了，会接到上面去所以在这里是 V 负，但它在下一个时间点呢，它就会过去从这边跑出来。注意这条线是什么？这条线上面会不会耗损能量？这条线不会耗损能量，为什么？因为本身线的描述它是无耗损的。然后呢，它左边是 open circuit， 右边是 open circuit。open circuit 跟 short circuit 都怎样？都是不耗损能量的。所以不止 open circuit、short circuit 不吃能量，事实上你只要是纯的 L、纯的 C， 你就拿纯的电感或电容来去做线路的 termination 的话，它也一样不吃能量。所以意思是说，假如有看过《阿凡达》电影吧？人类为什么要千里迢迢跑到阿凡达星去刨人家的祖坟？刨那些蓝色大精灵的祖坟，因为他们的祖坟是盖在一个东西叫做unobtainium 的元素上面。这个元素的特性叫做常温超导体，意思就是说在摄氏300度 K 左右，它就具有超导特性。所以我们只要从阿凡达星，不是那个星不叫阿凡达，叫潘多拉 ，OK 所以他们到潘朵拉星把他们的祖坟下面那块石头拿回来，把它做成传输线，你就可以得到这种传输线。那这种传输线是无耗损传输线。那无耗损传输线是什么效果呢？叫做无穷大的电池，懂吗？所以我们把无穷大的电池拿到那个地球上空的轨道，接一块太阳能板，它就可以把它充电。充多少嘞？反正你充的越久，它的电量就越多。OK， 然后嘞，你家就永远就不用再付电费了，这类的事情。这常温超导体浆，你要做到它可以来做无穷大的电池，好不好？那反过来讲，假如你用一个无穷大的，不是无穷大的电池，你用无耗损传输线，然后旁边都是整个线路上面没有 resistive 的 discontinuity、resistive 的 load 的话，那事实上讯号会在上面一直滚来滚去，一直跑来跑去，不会死翘翘，都在上面。那这边的话，我们看到的是 V 正的讯号 ，V 负的讯号，然后这个是对应的 I 正讯号跟 I 负讯号，所以你会看到 I 正讯号跟 V 正讯号怎么样？差了50倍嘛，差了一个 characteristic impedance。I 负讯号跟 V 负讯号嘞，差一点点，差一个负号，因为原本的那个式子的那个定义是负的 V0 over Z0，OK？ 好，那个So what happens? Suppose we wish to find the voltage and current distribution. In the previous slide, we already find out the current distribution at the t equal to 0. That is the beginning of the circuit analysis for this dual end open transmission line circuit. So so the problem continues with a specific time, that is t equals to 0.5 microsecond. With a certain time delay, which means the V plus signal and the V minus signal, the forward and backward going signal, will go in the transmission line for a certain amount of time. That then get reflected in the left end and right end and become the V plus signal may be part of the V minus signal, and the V minus signal, some of the V minus signal will become part of V plus signal. All right? So, however, since we already decompose the total voltage in terms of V plus, V minus, I plus, I minus, so we can continue our analysis with this specific time delay, that is 0.5 microsecond. And as I already mentioned, because the termination are open circuit, which absorb no energy, so all the incident power, all the incident signal get reflected, and the reflection coefficient at the two ends are what? Are positive 1 for voltage signal, and they are -1 for current signal. So remember to reverse the signal, all right? So the next step is to synthesize, to form up the V plus and V minus signal with the specific time delay, which is 0.5 microsecond in this case. Alright, so originally for the V plus signal, we can decompose it to A, B, C point. And for the V minus signal, you have a C and D. So with 0.5 microsecond, remember the total length of the transmission line is 1 microsecond. Okay, so only half of the signal, say from A to B, reach the right end and get reflected. So after 0.5 microsecond, A and B, the A to B part becomes part of the V minus signal because they get reflected from the right end. On the other hand, the BC section, the BC part, continues its propagation to the right and forms the leading edge after 0.5 second propagation, microsecond propagation. And also the CD part, which is originally the V minus component, with 0.5 microsecond time delay, they reach the left end and get reflected and forms the second half of the V plus signal as the CD component shown here. Okay, so with this shift in the time, with this shift in terms of time delay, in terms of propagation, you can form up V plus signal and V minus signal at t equals to 0.5 microsecond. Okay, 0.5 microsecond. And you can do the same to synthesize the I plus signal and I minus signal. However, the reflection coefficient of the open circuit for current are -1. Voltage reflection coefficient for open circuit is +1, and for the current is -1. So the two are the I plus signal and I minus signal after 0.2 microsecond time delay. And the very last thing is adding up the V plus and V minus power, I plus and I minus power to synthesize the total voltage and the total current. So as you can see here, the total voltage as the sum of the two piecewise linear function becomes this. The voltage is 0 at the left hand, 25 in the middle, and 100 in the right hand. And as to the total current, it becomes 0.5 and 0. Again, note that the boundary condition of 0 currents at the termination, at the end, is still satisfied for the delayed current response. Okay. All right. So the next problem, next condition we can check out with section 6.5 is the so-called arbitrary initial condition. 任意的起始条件. Suppose that we connect a resistor of value z sub 0 at the end of z equal to L at t equal to 0. The reflection coefficient at the end becomes 0 thereafter, and positive going wave at least impinging on the resistor goes absorbing the. Okay, let's check out the figure first. Wait, 我刚跳页了是不是? Oh, I'm sorry. I haven't finished the problem yet. Okay. Well, the description here is. 我跳到下一题去了，不好意思。好了，这边的描述是说本来我们不是有 V 正 IV 负讯号在这一个双端开路的传输线中间弹过来弹过去吗？所以我们刚才讲的说，题目一开始给你的是 total voltage 跟 total current。然后我们要把它找出 V 正 V 负，为什么要找出 V 正 V 负？因为 V 正的讯号就往右边跑 ，V 负的讯号往左边跑，跑到端点的时候被反弹嘛，所以你会形成新的 V 正跟 V 负讯号。所以经过了指定的 time delay， 在这个题目里头是 0.5 个 microsecond， 你新得到的是 V 正在 t 等于 0.5 嘛，跟它所对应的 V 负讯号，然后最后呢，再用这两个讯号合成起来，得到新的 V 跟 I， 对不对？得到新的 V 跟 I， 而这个新的 V I 就是 t 等于 0.5， 这边是 t 等于0，为什么？因为这个题目原本给你的是 total 的 voltage 跟 total current， 但实际上呢包含 V 正的成分，包含 V 负的成分，有左跑的，有右跑的，所以你先拆分开来之后，让它往左跑，往右跑，再来组合。那这一页的话是说，原本是双端开路嘛，然后我们又去蓝色大精灵的那边家里头弄了Aptenium 来去做出这个无耗群传输线，然后双端开路嘛，所以事实上能量在里头一直弹来弹去，但是不会死翘翘。但假如我们在某一个时间点给它加了一个 Z0 的负载电阻，那会发生什么事？原本在这个传输线上面的能量，这个传输线其实现在是等于一个电池但你加了一个负载之后呢，它会怎么样？把能量丢到这一个负载里头 ，dump 到这个 resistor 里头消耗掉，那会怎样？发光啊，发热啊， 反正消耗掉，所以 eventually 电池的那个能量会被耗损用尽了好，所以这边看到的说，假如你现在用的是一个匹配的负载的话，它就不会有反射波嘛所以它的下一个问题是说，要多久才能够把这些能量消耗掉？那不然各位有没有看到在前面的那个解答里头，其实有看到那个能量，事实上是像是什么？像是一列火车火车头是在哪里 ？A、B、C、D， 总长度是多少？1.5 microsecond， 就在这一个1 microsecond 长的传输线上面滚来滚去，对不对？所以假如在一开始的时候，你的右边把 open circuit 换成一个 Z0 的 matching node， 那么会发生什么事 ？A 到右边之后就被吸掉了 ，B 到右边也被吸掉了，然后呢 C 被吸掉，然后 D 被吸掉，总共要花多久时间？1.5 microsecond 嘛。OK， 所以从这个分析你可以看到，在这边滚来滚去的那个能量其实就是1.5 microsecond 长So the time for completed discharge into the resistor by the time of 1.5 microsecond with the resulting time variation of a time voltage across the load resistor as shown in the figure. Okay, so here we see if you place a resistor on the right end, so you will observe the incoming signal of A, then B, then C, and D, followed by D. And after that, all the energy is dumped or absorbed by the terminated match resistor. And there will be no more energy left on the transmission line. There will be no more energy getting bounced back and forth on this transmission line. Okay, so the very last problem that we will discuss in section 6.5 is the so-called uniform initial condition. For a line with uniform initial condition and current distribution, the analysis can be performed in the same manner for arbitrary initial voltage and current distribution. Okay, so here is example 6.6. What do you have with this problem? Okay, so let's consider a line of characteristic impedance of 15 ohm. Again, the length of the transmission line is 1 microsecond equivalent of 1 microsecond propagation delay. Initially, it's charged to a uniform voltage of 100 volt and 0 current. So this is a kind of a steady state or stable condition because the voltage is 100 volts everywhere, and because the current is 0 everywhere. So is there anything going back and forth within the transmission line? Well, no. Okay, well, you can simply put it's evenly distributed, is in a steady state, all right? And at this moment, the transmission line can be regarded as a capacitor. Why? Because you observe a voltage difference on this structure and no current. So at this moment, at this very moment, the transmission line behaves like a charge-up capacitor. And the energy is stored in terms of electrical field because you only observe a non-zero voltage. And on the other hand, the currents on the transmission line is 0 everywhere. What happens with this circuit? At t equal to 0, we will close up the left end and connect the left end with a resistor of RL. What is the value of RL? Well, it does not show up here. It's not necessarily the same as the characteristic impedance. Okay? So what happened? After the switch closed on, and if RL is not the same as Z sub 0, there will be a mismatch. That is, the voltage over current ratio across RL is not equal to the ratio of RL. because of a resistor says the resistor 100 ohm means that the voltage over current ratio should be 100 times. All right. So you will initiate a signal, say V plus, as well as the I plus, at this moment when the switch closes on, so that the initial condition can be, the boundary condition can be satisfied. So the boundary condition is what? Is that V sub 0 plus V plus should be 150 times of the I plus current. Okay, so initially you have 100 volt and 0 current. And because RL is 150, and the input impedance of the characteristic impedance of the transmission line is 50, so you need to satisfy this condition. So we can write up a few equations. Okay, so what do we have here? So assume that when the switch is closed on, we have a V plus signal and I plus signal as shown here. And because the transmission line characteristic impedance is 50 ohms, so we know that V plus is 50, I plus equals to 50 times V plus. And the total voltage over here is V sub 0 plus V plus, which is, so far as remember, is 100, I guess. And you can write out, because it forms a closed loop, so you can use KVL to write out the equation. And you write out as V sub 0 plus V plus equals to minus of I times I minus. Okay, so you may find a little bit curious, find a little bit strange about the minus sign. Why? Because the I plus signal is going to the right. And to form this KVL, we are starting from here, goes up and goes this way. So actually it's in the opposite direction of I plus current. So there's a reason why you need to put a minus sign over here. Alright? Okay, so anyway, we have this voltage over current relationship based on the boundary condition over here. And actually, how many are known in this equation? V plus, I plus, no, we actually have just one unknown, because I plus can be replaced with V plus over Z sub 0, okay? So here is the V plus signal, okay? So we can by substituting I plus as V plus over Z sub 0, we can write up this relationship. We end up with the description for the V plus. And by dividing V plus with Z sub 0, we get I plus. Okay, so now we can substitute the numbers. So say V sub 0 is 100 volt, the characteristic impedance is 50 ohm, and the load impedance is 150 ohm. You can calculate that the voltage, V plus voltage, is minus 25 volt. And the I plus current is minus 0.5 amp. Okay, and as I already mentioned, the I plus current is going to right or left, to the right by definition. However, you calculate the number of I plus is minus 0.5. What is the significance of this result? Well, the minus sign suggests that the actual current is going from right to left. And if you look at the physics of this configuration, you know that initially, before connecting to the load resistor, this transmission line is a charge-up capacitor. And when T is greater than 0, we connected a resistor to the left end, RL. So what happens? The capacitor starts to discharge energy into the resistor. Now, so the current flow is actually going to left, But that's okay. We can still determine the current as I plus because its effect is propagating from left to right. 也就是说 I 正电流。所以我们从物理上可以理解，因为你的 结构，这个充网电的传输线结构要往左边的电阻去释放能量，所以你的电流应该是从传输线流到电阻上面，所以实际的电流流向应该是从左边到右边的。但是从电路分析的春训的站态电路分析的观点，我们可以看到，当开关关上的时候，它的影响是从左边影响到右边的，所以你还是可以定义所谓的一个 V 正 I 正的讯号，因为这个 V 正 I 正的讯号，它们的影响是从左边往右边影响的，虽然实际上你算出来的这个 I 正的讯号值是负 0.5 安培，表示说，这电流其实是从传输线流到电阻上面的，但是只要你那个负号标对，这个描述还是合法正确的 ，OK， 所以从这个结果我们可以看到，虽然我们在标的时候说，你是一个 V 正电压 I 正电流，但实际上它是能量是从传输线丢到这一个结构上面的，And here's the follow-up bouncing diagram analysis for this case. So we know that once the switch closes on, the charge transmission line, which acts like a capacitor, starts to dump energy into the resistor to the left. So the initial voltage signal V plus is minus 25 volts. So the effect, the V plus signal will propagate to the right, and with 1 microsecond, it will reach to the right end, and it will generate a reflected signal because the reflection coefficient at the right end is 1. Okay? So the total voltage observed on the right end initially is 100 volt before seeing the V plus signal. After that, it becomes 50 ohm because there is 100 minus 25 minus 25, so it's 50. And the minus 25 signal will go to the left end at t equals 2 microsecond. And because the transmission coefficient is minus 1/2, which means part of the signal gets reflected and part of the signal or part of the energy is dumped into the resistor continuously. So here we have a reflected signal of minus 12.5, that is minus 25 times 1/2. And at 3 microsecond you reach the right end, it gets reflected totally because the reflection coefficient is 1. So the minus 12.5 signal reached the left end again at 4 microsecond. And this time the signal size is diminished by half again as minus 6.25. And get reflected again. And so as you can observe, signal becomes smaller and smaller, which means more and more energy are dumped into the resistor to the left. So eventually, all the signal, all the energy stored in the transmission line will eventually dissipate to the low resistance to the left, right? When we observe the total voltage at the left end starting from 75 volts, that is 100 minus 12, and diminished to 37.5 at the 2 microsecond, becomes 18.75 at 4 microsecond, and cut half every 2 microsecond. And this figure also suggests what? Suggests the energy dissipated on the resistor. So in the next slide, we will examine this example in terms of in the perspective of energy. So we will first calculate the energy stored on the transmission line, which can be divided into two parts. One part is the energy stored in terms of capacitor, and the energy stored in terms of inductor, which, well, the capacitor and inductor are used to analyze the problem using circuit terminologies. 所以我们就用电流 电感跟电容的话，是用电路学的语法来去描述这一个传输线上面所储存的能量。那你假如从电磁波的观点的话，这个应该叫做电场储存的能量跟磁场储存的能量。所以还记得我们的一些对比吗？电场所储存的能量，磁场所储存的能量是电感，那相当于是电感所储存的能量。那电容所储存的能量其实是等同于电场所储存的能量，好不好？好，所以在下一页里头，我们可以看到它的类比分析了哈。So here we have two equations. One is the energy stored in terms of electrical field, and energy stored in terms of magnetic field, which can be decomposed as, or which can be represented with energy stored in terms of capacitance and stored in inductance. So with some substitution, due to the limitation, I encourage you to look at it yourself. You can end up with this representation. So the total energy on the transmission line can be represented as 1/2 times V to the square over Z sub 0 times the length of the transmission line, which is equivalent to the time delay on the transmission line. So here's the representation of energy stored on the transmission line in terms of capacitor, wire capacitance and electrical field. And here's the energy stored in terms of magnetic field, or the energy stored in terms of inductance. And for this case, because initially we have 100 volt distributed evenly on the transmission line and the current is 0, so the magnetic energy stored in the transmission line is none. All the energy stored in the transmission line are stored in terms of capacitance. So we can calculate the energy WE using this equation, and if you put it into the numbers, it equals to 10 times 10 to the minus 4 joule as energy, 10 to the minus 4. And you can also calculate the energy dissipated. You see, here we have WD. D represents dissipation, power dissipation. So it can be found as an integration over time. So you have V squared over R. That is the energy. With the time integration, that will be the power, the dissipated power with the time integration becomes energy. So we have first section, second section, third section, and again you can see that this is an infinite series. And when you do the math, you will find out that the energy dissipated on the resistor is 10 to the minus 4 as well. So we have a balance. You can satisfy the energy balance in terms of stored energy and the energy dissipated on the resistor. The energy the energy dissipated on this termination resistor. All right, so here is